Okay, welcome to the third part of our regularization and regression lecture. Now we have in the last part defined our objective to get sparse regression vectors. And the question was, and how do we optimize this? And the result was we actually have no clue. So we actually cheat a bit and we tweak a bit our constraints and our objective functions that we actually arrive at something which is easy to calculate and to optimize. And now we will have a closer look at this. So how do we actually do this? So what we first do is now we apply the penalization term of the squared L2 norm, which is really nice to optimize because the L2 norm to the square is smooth. So this defines our task of rich regression. So we have here again, given what we have already established, which is necessary for our regression task. So we have our data matrix D, a target vector Y, the design matrix X, and a regularization rate lambda. And now the task is to find the regression vector beta, which solves the following objective. And here we see now our penalization approach. So we minimize the residual sum of squared plus our regularization rate lambda times the squared norm of beta. And then we return our predictor function after we have optimized this, which is equal to phi from x transpose times beta. So our objective here is unconstrained and smooth because we have the smooth residual sum of squares term plus lambda times the smooth squared norm of beta. Okay, so let's have a look how we can optimize this. So our rich regression objective is smooth and it is convex because it is a weighted sum of convex functions, and we had already in the optimization lecture that this is then also returning a convex function. So that means that we again only have to compute our stationary points, and this derives or delivers then our global minimizers. So the computation of the gradient uses here only the linearity of the gradient, and we have already derived in the optimization lecture the gradient of the residual sum of squares and of the squared L2 norm. So then we get this gradient here and we set it to 0, and then we try to solve for beta. And what do we get here? First we multiply this term out here, so then we have here minus 2x transpose times y plus 2x transpose x times beta plus 2 lambda beta, and this is then equal to minus 2x transpose times y plus 2 times x transpose times plus lambda times beta, right? So here we applied the distributivity, and then if we set this equal to 0, then we can add here 2x transposed y and divide by 2, and what is standing there is then x transposed x plus lambda times beta is equal to x transpose times y. And this is exactly what is standing here. Now we have again this problem or the case that we would want to solve for beta, and we can do this if x transposed x plus lambda I is actually invertible. So does this bring now everything? The answer is actually yes, because the matrix x transposed x plus lambda I is invertible, and we can derive this by the singular value decomposition. So given that x has a singular value decomposition u times sigma times v transposed, then we can derive that x transposed x plus lambda I is equal to v times sigma transpose sigma plus lambda I times v transposed. And now again, this matrix here determines if this whole matrix is invertible, because if sigma transpose sigma plus lambda I is invertible, we can denote here the inverse. Do you know what it is? Let's leave this for an exercise. We can also discuss this in the lecture, and maybe I will put this in the math PDF. But now important is that this part here, sigma transpose times sigma plus lambda I, is actually invertible, and this is the case because our matrix sigma transpose sigma plus lambda I has this form. So first sigma transpose sigma is sigma 1 square until sigma r square, where sigma r is the smallest singular value which is not equal to 0, and the rest is here all 0. And if I add now lambda times the identity matrix, so this is the matrix which has lambda on its diagonal, then I get here sigma 1 squared plus lambda on the first diagonals, on the first r diagonals, and it's lambda all the way down, right? Like this. And this matrix here is now invertible because it has only non-zero elements on the diagonal, so all these elements are invertible. So this is really cool. For every lambda larger than 0, we get now a uniquely defined beta, a uniquely defined global minimizer of our ridge regression problem, which is defined as it is here. Now, the ridge regression minimizer is actually connected to the regression minimizers we have derived by SVD. So if we have the SVD of our design matrix U sigma V transposed, then the ridge regression solution beta L2 with a small regularization rate lambda larger than 0 is similar to one of the global minimizers of regression. So we had just derived that beta L2 has this form here. Now if we insert for x the singular value decomposition, then we get here this form. And then you see, if you compare this with the solution vectors beta we had for the regression problem, that this is equal to the beta if we say that this here is our matrix A. And then we have here this formula VA sigma transposed U transposed Y. And this was in the set of our optimizers beta, which solved the regression task. Now if you have a look at this, so if lambda larger than 0 is small, and A is here now given as is depicted here. So on the top left we have our invertible part of the singular value decomposition for those singular values which are actually larger than 0. And then we put here in the lower block diagonal here 1 over lambda. And this is here our definition of A, and actually this part here, sigma transpose sigma, is equal to A, only that we have here in the denominator a plus lambda. So if lambda is small, then this term here is approximating the singular value, and then we have here our regression solution, also approximately equal to ridge regression. So yeah, let's have a look at our toy example. What happens now if we apply ridge regression? So we have here plotted the results for the given regression parameters. So first we have here in blue beta plus, which is given by the singular value decomposition. So this is this one here in blue, beta plus. And then we put the lambda on a bit. So we put here now lambda equal to 1. Then we get this solution vector. This one is in red, and you see already that this is similar to the original SVD solution we got for the residual sum of squares minimization problem. And then if we put the lambda even higher, then we get values which are for beta smaller and smaller. So you see here from beta plus is a bit like our starting point. So here we have 1.6, and this becomes then to 0.8, and if we put the lambda even higher, then this is here a 0.2. And you see here that now this function beta L2 for lambda equal to 20 is actually not approximating the points we have so well anymore. So this is the effect of regularization. Of course, the higher you put your regularization rate, the more you get simple functions. The most simple function is here the function which returns just 0 for all points. And this is where these regularization solutions are converting to the more we increase lambda. But that is not really solving our problem here now, right? Because we actually wanted to obtain sparse regression vectors, because this would then perform a selection on the features we actually need. But we do not get a sparse solution here. all of the entries for beta L2, even for lambda equal to 20, which is actually quite high. The function does not approximate our points so well, but still we do not get the sparse solution. So this is not really solving what we want. I mean, it's nice that we get now a uniquely defined solution for our regression vector, but it is not really delivering us the sparse result here that we were looking for. So this concludes now our third part for this lecture, and in the last part we will discuss the lasso which employs an L1 regularization term. See you then.